Hey everybody, this is Mr. Sheeline here. This is going to be the video lecture notes covering the Unit 7.1 notes, where we're going to be taking a look at the heating and cooling curve diagram and kind of make sense of all of it. So just real quick, that's what we have here. We've got the heating curve diagram. We also have a cooling curve diagram, which pretty much, they work exactly the same way for the most part. Obviously, the only thing that's different about them is that one, here we are increasing the temperature at roughly about the same amount, and we're seeing what kind of phase changes happen over a period of time as we increase the temperature. And then for the cooling, it's just the opposite as far as temperature goes. We are watching how, starting with a gas, when we decrease the temperature, we're watching how or where we see phase changes. We are seeing how they change.
Mrs. White, please come to guidance. Thank
Sorry
you.
about that. How they change over time when we decrease the temperature of a given, system. So let's just kind of jump right to it then. So real quick though, just keep in mind, I'm realizing the structure of this is a bit wonky. Really, cooling curve should be down like right here. This material here is going to apply basically to both of the pictures here. Supercooling is really just going to be looking at this, and it's just a cool little phenomenon that we can take note of. But for the most part, yeah, this just is applied to both of them. So, okay. So here on the heating curve, well, what is a heating curve? It's a diagram here showing the temperature change over time for a substance as it goes through phase changes. So things that we have to recognize is that it is temperature versus time versus temperature, depending on how you title it, but really our y-axis variable here is going to be temperature. The time variable is going to be on the x-axis. So how do we make sense of what's happening here? So we make sense of it by basically just watching what is happening. So again, remember, we are increasing temperature to the substance over a particular amount of time. Okay, so we see here on these nice little slopes here that as we increase the temperature, okay, we're going from a solid to a liquid to a gas, okay? But what should be kind of striking and what should stand out to you is the fact that, oh, that's kind of weird. Look at that. It's like when we are going through a phase change, our temperature does not change, okay? Our temperature does not change. So we see again, these slopes here, we have a change in temperature. So when we have a substance that's a liquid, whatever this temperature is, so it's going to stay liquid from here to here. And then when it reaches that particular temperature, it then begins to go through a phase change from a liquid to a gas. And then after it's finished that, it then goes into, and it becomes a gas. Okay? And that's the same thing with a solid down here. Okay? And it's important to recognize this because it tells us how the energy is going in and out of these systems. It's telling us what exactly is happening, or at least it gives us a hint of what's happening. And so if it's not obvious, maybe we'll talk about it. So during a phase change, the temperature of the substance does not change, and we see that. So again, whatever this temperature is, like right here, so whatever that temperature is right there, when the solid is transitioning, when it is going from a solid state to a liquid state, it maintains that temperature. Whatever this temperature is, it stays at that temperature. And we see the same thing when we go from a liquid to a gas. So whatever this temperature is right here is where we see it go from a liquid to a gas. And it doesn't increase or decrease its temperature. It stays about the same. Okay. And when we see this happening, what is happening? So when we reach this temperature, we will see melting. When we increase, and then after it's done melting, we'll increase the temperature continually. And then it gets up here, and it's going from liquid to a gas, and it's going to do that via vaporization. Okay. Now, if we start up here, like the cooling curve does, if we start up here, then we go down, then it's condensation, then it turns into a liquid, and then when it goes from a liquid to a solid, it's freezing. Okay, that sort of thing. But what is happening to the energy? So what is happening to it? So, however, during a phase change, the energy of the substance changes. Either it's gained or it's lost. So here, energy is used to, and that should say affect, not effect, but affect. affect the intermolecular forces. And remember, those intermolecular forces allows the molecules to fall apart or get closer together. So when we are increasing our temperature here, when we are increasing the temperature, and when we're going from, say, a solid to a liquid, so what's happening to the energy? So and let's see where to write this down at. So as a note to write down here. So we'll describe what the energy is doing when we're looking at just like E right here. So from here to here, what's happening to the energy? Well, the energy is increasing, which means that kinetic energy is increasing, which then means that the motion of particles is increasing. Okay. So we can say that for right here as a gas. We could say the same thing for the liquid. We can say the same thing when it is a solid. Okay. Again, as the temperature increases, it's the opposite when the temperature is decreasing. Instead of energy increasing, energy is decreasing. Kinetic energy decreases. Motion of the particles decreases. Okay. So then what's happening right here? What's happening during the melting and vaporization? Well, what's happening is that, and this is why we see this little slough of we're seeing here, or I shouldn't say slough, but we're seeing the substance maintain a particular temperature. So what's happening? Well, what's happening is that the energy is being stored as potential energy. So the energy is being stored as potential energy. Okay. So we can say that, and this is the bigger point, and then we also see particles moving further away from one another. Okay. So we see all this happening. So here at melting and here at vaporization, what the energy is doing is that the energy being stored is being stored as potential energy. There is no and that's why again we see this temperature just stay the same, and the particles are now moving further and further away. Think of it like when you watch an ice cube melt. I mean, does the ice cube almost now, and maybe this is a bad example because we should know that when it freezes it does expand, like ice expands when it freezes, but for the most part, we think of like, oh, well, they're like it's separating. They're getting further, like the particles are a bit looser. They're not as tightly bound together. They're moving further and further away from one another. So you can think of it in that way as we're melting it. And then even they moving further away when we go from, if you boil the water, let's say, it's going from the liquid to the gas. The particles are moving further and further and further and further away from one another. Okay. And again, we see basically the same thing with the cooling down here. The only difference is just a couple of things. So we still see that temperature stays the same when we are going through phase changes. Okay, and then at whatever temperature it's supposed to reach. And then when the substance is cooling, when the energy is in this case being released here, when it's losing energy, we see that happening up until the phase changes. Okay, we see that up until the phase changes. So here when we're cooling a gas, energy is decreasing, and we'll even say, I'll just add in kinetic energy. Kinetic energy is decreasing, and what that's doing then is also that the motion of our particles, motion is slowing down. It's decreasing. Okay, there's not as much motion compared to what it used to be. Okay, and then we can say that to pretty much all these things right here. So when it's cooling solid, when it's a cooling liquid, same thing. Kinetic energy is just consistently it's decreasing, and we see that as the temperature decreases over time. Okay, and then what we see at the condensing and then the freezing, we're seeing here that the energy. Okay, so here the energy isn't being stored. It's not absorbing energy. Energy is lost during the energy is lost during phase change. Okay, and not only that, and particles are now moving closer together. Okay, particles moving closer together. Okay, so we see all this happening. Particles are moving closer together. Okay, and that's what we're seeing here at condensing and also at freezing. Okay, now there's this weird little thing that I'll add in before we go into the backside. What is this little thing? Well, it's just supercooling. So supercooling is this neat little thing about, and it's a little exception of what's happening, but it's where a liquid is cooled to a particular temperature below its freezing point. And so the freezing point for whatever this substance is would be the temperature in which it would, so whatever, if you're reading this graph, it'd be whatever this temperature is right here. So it's supposed to freeze when it reaches this temperature, but for whatever reason, and really the reason is whatever the crystallization point is of the substance, if it's not exactly met, if it's not arranged, so if the physical thing is not arranged in a particular way, or if you've added, sometimes you can do it by adding a particular substance, say salt to water. You can do it with salt to water. More or less what happens is that the salt kind of breaks up, or it throws, you could say, like throws a stick in the wheel of water's bicycle. It kind of stops its flow from going from a liquid to a solid, and it keeps it as a liquid. But all it takes is basically just someone to take the stick out of the wheel of let's say of water's bike. I know this seems kind of silly, but as soon as we take that stick out, then the water can then go from a liquid to a solid. And basically what we would do, that would be the equivalent of taking the stick out, would be either flicking it, like if we literally just went like bop on a bottle of water that was super cooled, it would instantly begin to freeze. Or what we can do is carefully pour it out of a bottle onto relatively cold surface, and it would begin to freeze as it's being poured out. You'd see it, basically you'd see like instant snow being made right in front of you. And we'll see that in class, okay? And that's all supercooling is. And it's a neat little thing that happens to some substances. Again, if you kind of disrupt basically the lattice system of the water, if we're talking specifically about water. Okay, it does happen to other substances too, though. But anyway, so that's how we read these graphs. This is how we read these diagrams. Let's just say, like, well, here's the temperature in which this substance is going to condense. It's going to stay at that temperature until it's all done condensing, and then it's going to decrease its temperature again. Okay, and the same thing, only just different direction for heating. Here's the temperature in which it's going to go from a solid to a liquid. Here's the temperature which is going to be our melting point. And then here is the temperature in which, and actually that's actually a good thing to write. So this is melting or melting point. It's a very specific temperature. And we'll get more into that as we go along. And then here, vaporization, this is called boiling point. Okay. You can say that's freezing point, and then that's point of condensation, if I remember correctly. There's no like liquid point. So anyway, so a whole bunch of stuff to add, a whole bunch of notes. And then on the backside, so then we have here on the backside a diagram showing how pressure and temperatures are related. So before it was just temperature and time. This is going to be how pressure and temperature are related to one another. And this has to do with something, this has to do more with what's referred to as the ideal gas laws that we don't really get into in Chem, in Chem 1, but you definitely get into in you get into that in Chem 2. So we're just going to take a look at what the relationship is between pressure and temperature with particular substances, just in this way. So as we see here, there's something to do with pressure, there's something to do with temperature. They're somehow related to one another. They clearly have something to do with one another, especially when it comes to how a particular substance will basically go through a phase change. So here over in this area, if we have a particular temperature at a particular pressure, that substance will be a solid. So let's say that of the substance, our temperature happens to be right here, and the pressure happens to be right here. So wherever those intersect, wherever they meet up, will tell you what the state of the substance should be. Okay? But then we've got these weird lines here. So what are these weird lines? So these weird lines is where we would see phase changes. And that's what's depicted on here. So let's say like right here. So if I'm meeting right here, so whatever this temperature is, whatever that pressure is, if we were to set that temperature and that pressure at that point, whatever the substance is, if it was a solid, it would begin to melt and it would go through a phase change from a solid to a liquid. It would begin melting. It's its melting point. If, let's say, it's in a liquid and we maintain the pressure, but then we are increasing the temperature, okay, at whatever temperature this is, we would see a phase change from liquid to a gas, okay? And so this is all it's saying. So it's really just plotting out. So it's like, again, let's say we have this amount of pressure, and let's say we have this temperature here. Okay, what state of matter is it in? We'd say, well, we're going to see where those meet up. So that's going about right there, and that's going to meet right there. Our substance should be a liquid if it meets right there. Okay, that's how we read this. Okay, and usually pressure is going to be in what's referred to as atmospheres or ATMs. Okay, it's just so here at what we'll say is roughly sea level, we are sitting and breathing air that's at 1 ATM. And so when you decrease, or when you go, like, say, if you go underwater, you're increasing ATMs. As you get closer and closer to the, or as you climb up higher, say, like on a mountain, you are decreasing the pressure of the particular ambient air that you're breathing in. So we measure them in ATMs. We also measure them in pascals. Just depends upon the scientist and specifically what you're trying to measure. But anyway, just to recognize that we measure in ATMs and atmospheres. So anyway, okay, so what about, there's some stuff, gobbledygook up here. What does this all mean? So this is what we say is a phase change diagram, where it is specifically related to the pressure and temperature relationships between, or with the relationship between pressure and temperature on a particular substance. Okay. Now there's something called an equilibrium curve. So this is the line on a phase change diagram that indicates a change from one state to another. So all these little lines here, so this line right here, this line right here, and then this line right here, all those lines, so this one, and this one, those are all equilibrium curves. This is where if we were to, again, put our temperature here at this pressure, we would see a solid go to a liquid, or we'd see a liquid go to a solid. Okay, that's all those are. Then you have a triple point. Well, it's a triple point. So if we could maybe deduce what that is, we notice that this is somewhere between a solid, a liquid, and a gas. So like it's right where all three intersect. And so a triple point is that, it's just that. It's a point on a phase change diagram where the substance exists in all three states of matter all at the same time. Okay, so a substance, even if you start as a solid, let's say, you get to the triple point, you will see it as a solid, or change between a solid, a liquid, and a gas all at the same time. Okay, and then there's the critical point that's all the way up here. Okay. And the critical point is a point on a phase change diagram where the liquid and gas states have nearly identical densities and cannot be distinguished from one another. So again, it's kind of like triple point, but up here it's more of like it's going just between liquid and gas back and forth constantly. And at any given moment, you don't know exactly how much gas you have, or at least you're not able to know exactly the amount of gas you have per versus liquid, just because you don't have, they change so quickly and rapidly between one another. Okay, and that's all critical point is. So you've got this special spot, you've got this special spot. We're going to be looking at this specifically in class, not so much this, but we're going to be we're going to be practicing how to read all this. And I'll have a video that will show how to walk through a particular assignment that we did in class. But other than that, that's pretty much the notes here. So anyway, those are the notes for the 7.1 notes. If you guys still have any questions for me, make sure you ask. If not, I'll see you all in the next one.